All right, so the next example is going to be a curve sketching problem where we have an oblique asymptote, and we're going to see how that specifically behaves. So when we're talking about curve sketching, the first thing we want to try and identify is our asymptotes. And so let's start with our vertical asymptotes. We have a vertical asymptote where our denominator equals 0, because if we divide by 0, then we get dne, so that means we're going to have a vertical asymptote there. Or holes will happen when you have two terms that cancel out in the numerator or the denominator, but there's really no way to factor this or rewrite it so that we get two terms to cancel. So wherever our denominator equals 0, we're going to have a vertical asymptote. So 9 minus x squared equals 0. So let's see where we have our vertical asymptote. We're going to get 9 equals x squared. So the square root of 9, or plus or minus square root of 9 equals x. So then x equals plus or minus 3. So those are going to be our two vertical asymptotes. We're going to have a vertical asymptote at x equals -3, and then a vertical asymptote at x equals regular 3, positive 3. So now we're going to look at our horizontal asymptotes or our oblique asymptotes. We have a horizontal asymptote when the degree on top equals the degree on the bottom. And we have an oblique asymptote when the degree on top is greater than the degree on bottom by 1. So, in this case, our degree on top is 3. We are talking about the highest powered term of x. So the power of our numerator is going to be 3, and the power of our denominator is going to be 2. So we have an oblique asymptote. So what we're going to do is then we're going to go 9 minus x squared into x3. We are doing polynomial long division here, and I'm actually going to rewrite this as negative x squared plus 9. It's just going to make the division easier. How many times does negative x cubed go into x? How many times does negative x squared go into x cubed? That's going to be negative x times, because when we multiply negative x by negative x cubed, we are going to get x3, and then that is going to be minus 9x. Then we are going to switch the signs on both of these, and then this x3 is going to cancel with this negative x3, and we are going to be left with just 9x. How many times does this go into 9x? 0 times. We cannot put that in there, so then that means we are done, and we have our remainder, which we write as 9x over this thing over here. So this is our answer, but the cool thing is, for the purposes of oblique asymptotes, we don't care about this at all. We only care about this negative x. So we say our oblique asymptote is y equals negative x. Okay, great. So now we found our asymptotes. We got two vertical asymptotes and an oblique asymptote. So then let's talk about our domain. And there's a reason why we talk about asymptotes first, is because vertical asymptotes heavily impact our domain. So a normal function would have a domain of negative infinity to infinity. But when we have vertical asymptotes, it fractures that, because we are undefined at vertical asymptotes, right? Because when we plug in 3 or negative 3, we're dividing by 0 and we get undefined. So we've got asymptotes there. Those points have to be excluded from our domain. So let's just exclude those points from our domain. So we go from negative infinity to negative 3, and then negative 3 to 3, and then 3 to infinity. So basically, we just not x equals negative 3 or 3. We're just excluding those from our domain. Cool. So now we have our domain. So the next thing we need to do is we need to look at intercepts. And then we have x-intercepts, and we have y-intercepts. X-intercepts are places where f of x equals 0. So we set our function x cubed over 9 minus x squared equal to 0. And that's going to equal 0. We can multiply both sides by 9 minus x squared to just get x cubed equals 0. And then x equals 0. So we're going to have an x-intercept at 0, 0. Okay. And then for y-intercepts, that is going to be where we just plug in 0 to our function. So we're going to get 0 cubed over 9 minus 0 squared, which is going to be 0 over 9, which is just 0. So then we can say that we have a y-intercept at the point 0, 0, which makes sense, right? If we have the origin is both an x-intercept and it is a y-intercept. Okay, great. So now that's actually all of the information we need from our base function. So now we're going to take our first derivative, and a lot of times you'll be given the first derivative and or the second derivative. I'd say you're more likely to be given just the second derivative, but we'll see. So it's just for the sake of time. It's a messy quotient rule, the derivative of our base function. So, they want to see your ability, generally speaking, they want to see your ability to handle curve sketching problems, not necessarily quotient rule problems, right? You've already been tested on that. So sometimes, unless the derivative is kind of easy, you will be straight up given your f prime of x and your f double prime of x. So we need two main things from our first derivative. We need intervals of increasing and decreasing, and we need maxes and mins. So where do we have increasing? Our increasing is where our first derivative is greater than 0, and decreasing is when our first derivative is less than 0. So what do we need to do for this? We need to make a sign chart. And remember, critical points are wherever our derivative is 0 or does not exist. So where does our derivative equal 0? When our numerator equals 0. So x squared times 27 minus x squared equals 0. So we can divide both sides by x squared to get 27 minus x squared equals 0. So 27 equals x squared. X equals plus or minus the square root of 27. So we know those are going to be 2 points on our graph. So now we want to see where f prime of x does not exist. And that's going to be when our denominator equals 0, right? Because then we'll be dividing by 0, and we can't do that. That gives us undefined. So we set x squared minus 9 squared equals 0. So we can square both sides. We get x squared minus 9 equals 0. X squared equals 9. X equals plus or minus the square root of 9. So x equals plus or minus 3. So we get negative 3, and we got 3. So now we want to plug these in. And one thing that we can notice is this term is always going to be positive. Because if you square a negative number, you get a positive number. If you square a positive number, you get a positive number. If you square 0, you get 0. So this is always going to be positive. And so is this term, because any term that you square, or any term that you take to an even power, take it to the second power, the fourth power, the sixth power, the eighth power, you're always going to end up with a positive number, right? So this term is always going to be positive, and this term is always going to be positive. So the only term that we're really looking at is this 27 minus x squared. And if we plug in something to the left of negative 27, say we plug in negative square root 28. That's 27 minus 28, because a negative, if you square a negative, you get a positive, and that's going to give us negative 1. So we're going to get a negative number out here. Say we plug in something between negative 27 and negative 3. So we plug in negative 1. That's going to give us 27 minus 1, which is a positive 26, right? So we're going to be positive here. Say we plug in something between negative 3 and 3. Say we plug in right 0. 27 minus 0 equals 27. So that's going to be a positive 27. So we are positive there. And then same thing for 3 to 27. We're just going to plug in 1. Say 27 minus 1 is 26. You get the picture, positive. And then 27, say we take, positive square root 28. 27 minus 28 is going to be negative 1, which is going to be a negative number. So we're going to be negative on that interval. So that's our sign chart. So now we should label these points on our sign chart. So any point that we get from our numerator, so, because we solve for our numerator and our denominator equaling 0. So when we solve for our numerator equals 0, which we did here, and it gave us plus or minus the square root of 27, that is going to be a potential critical point, or that's going to be a critical point. So that's going to be from decreasing to increasing. That's going to be a min, and then positive square root 27. From increasing to decreasing, that's going to be a max. So, and these points, -3 and 3, they are not maxes nor are they mins, because we got them from trying to find where our function does not exist, right? We set our denominator equal to 0 to find those points. So these are actually vertical asymptotes because we got them from setting our denominator equal to 0. They cannot be maxes nor can they be mins. Only points you get from setting your numerator equal to 0 can be maxes or mins. So we have a min at x equals negative square root 27, and we have a max at x equals square root of 27. So, okay, great. So on a test, you may be asked to plug those back in to find the y values of these. And we're not going to do that just in the sake of time. But just keep in mind that you're going to be plugging them back into our base function. So you use your first derivative to find the x values that you're talking about, and then you're going to want to plug them back into your regular function, not your first derivative. So just note how we're plugging them back into f, not f prime. Just note that. Okay, so we have our mins, we have our maxes, and we have our, well, actually, no, we need to close out our intervals of increasing and decreasing. So let's start with decreasing. So since we're on this interval from negative infinity to negative root 27, we're decreasing, and then we are also decreasing, right, from square root 27 all the way up to infinity. Okay, now we are increasing from negative square root 27 to negative 3. And then we're increasing again from negative 3 to 3. And notice how we are excluding the vertical asymptotes here. We are not including them in our intervals. So then from 3 to square root 27. So this is going to be our intervals of increasing, decreasing, and our maxes and our mins. All right, so now the only information we have left to compile is going to be stuff from our second derivative. And the second derivative is going to be this function. And what we care about with our second derivative is we care about inflection points, and we care about concave up and down. What intervals are we concave up on, and what intervals are we concave down on? So, and we need to make a sign chart for this as well. So, kind of similar to our first derivative, we start by setting our numerator equal to 0 to get our critical points there. And we can see that if we plug in 0, we get 1. And if we, so this can never be negative, right? Because if we plug in a negative 1, that becomes a positive 1, and that doesn't really do anything for us. So this can never be negative since you have that x squared. So since this can never be negative, it can also never be 0, right? There's no way for this term inside the parentheses to ever be equal to 0. So we can't get a 0 from that. So the only point, at least from our numerator, is going to be 0. And then our denominator, we can set that equal to 0. X squared minus 9 cubed equals 0. So we can take the cube both sides. We get x squared minus 9 equals 0. X squared equals 9. So we're going to have x equals plus or minus the square root of 9. So x equals plus or minus 3. Fantastic. So we're going to have negative 3. And we're going to have 3. And this is going to be the points on our sign chart. And let's just notice right away, right? We got this from our denominator, and we got this from our denominator. So these are going to be vertical asymptotes. We got this from our numerator. So this is going to be either a max, a min, or a straddle, right? Straddle is where it's either negative, negative, or positive, positive. Maxes and mins are where they switch on either side. Okay, so now if we plug in something to the left of negative 3, we get a negative here. This is always positive, right, this term, because we can never get that x to be negative, so we can never get this 27 to be 0. And then down here on bottom, if we plug in a negative 3 or something to the left of negative 3, we are going to get a positive number. So then that is going to be positive, or yeah, wait here. So that's going to be negative, because this is going to be a positive, right? Positive times a negative times a positive. So that's going to be negative. Something between -3 and 1, so say like -1. This term is going to be negative. And this term is also going to be negative. So we get a negative times a negative, which is a positive. So then something between 0 and 3 could be like 1. This is going to be negative. This is going to be positive, so that's going to be a negative times a positive, which is going to be a negative. And then something to the right of 3, so we could say we could plug in like 4. That's going to give us a positive here, and then a positive here. So that's going to be positive times a positive times a positive, which is going to give us this. So our 0 is going to go from increasing to decreasing. So that's going to be a max. And then our 3 and our -3 are vertical asymptotes, right? So they are neither maxes nor are they mins. So, these are not maxes or mins. We're talking about the second derivative, so it is an inflection point. So inflection points are just places where our second derivative goes from positive to negative or negative to positive. So we have an inflection point at x equals 0. And so you could plug this back into your base function to see what you would get. And then our intervals of concave up is going to be where our second derivative is positive, so it's going to be -3 to 0, and then again from 3 to infinity. And then we're going to be concave down where our sign chart says we are negative, so that's going to be -infinity to -3, and then again from 0 to 3. Okay, so we got our concave up, we got our concave down, we got our inflection points, and we got all our base stuff. So let's construct our graph. This is the last part. So I like to always start with my, where are they? My intercepts. So our only intercept is going to be 0, 0, which is also, funnily enough, going to be our inflection point. All right, so now let's talk about our asymptotes. So we got a vertical asymptote at -3 and 3. So I'm going to put a vertical asymptote there. And then a vertical asymptote here. And then remember, we have a oblique asymptote. Here, I'm going to write this. X equals 3, x equals -3. And then remember, our oblique asymptote is negative x. Okay, so we got our asymptotes, we got our intercepts. Great, so now we're going to plug in our maxes and our mins. So where'd that go? Okay, so we've got a max, right, at square root 27. Square root 27, so remember square root 25 is 5, so square root 27 is like 5 and some change, something like that. We are going to expand this out and put a maximum, and without plugging in this, we really don't know what our minimum is at. I'm just going to assume it's something like this. We'll say it's like this. So then, same thing for negative square root 25, or negative square root 27, but that's going to be a min, right? So we'll put that one down like here. And so now we have our inflection points, we have our maxes and mins, and then now we can use our intervals of increasing and our intervals of decreasing to fill in the gaps. So we know that from negative infinity to negative square root 27, we are decreasing. So we could say we're like coming from here. And remember, we follow that asymptote. And then we switch to increasing. And then we are going to switch to increasing from negative square root 27 to negative 3. We're going to be increasing. So that's going to come from up here then. Check it one more time, negative 3. So negative 3 is going to be a vertical asymptote. Oh, yeah, that makes sense. Okay, yeah. So then from negative 3 to positive 3, we are going to be increasing. Okay, cool, yeah. So we're going to do something like this. Okay, great. And then now from 3 to square root 27, we're going to be increasing. And then from square root 27 to infinity, we are decreasing. And we're going to follow that asymptote.